On the chapter 6 review. Before I get into that, this is kind of the end of the semester for us. Um, After this chapter 6 test, you could be done. If you need some help determining what your grade would be if you skip the final, I can help you do that. The final is completely optional test. Definitely, if you miss the test, you'll need to take the final. Probably, if you have a really low test, you might have to take the final as well. But after I grade your Chapter 6 test, I'll be able to tell you what your grade would be if you skip the final and what you'd have to get on the final to improve your grade. The final can't hurt you no matter what you get on the final. If it doesn't help your grade, I just won't count the final, so it can't make you go lower. For some of you, this is your last math class. At least you want this to be your last math class. And that's fine if you know for certain you're never, ever going to go for a 4-year degree. If somewhere's in the back of your mind you think at some time in your future you might want to get a 4-year degree, intermediate algebra won't count anywhere in the country for a 4-year degree. So you need to take at least one more math class to have the shot at getting a bachelor's degree without having to take more math. If you take time off of math and say 5 years from now decide you want to get your bachelor's, they're going to make you take a college algebra type course, and it'll be heck to pass that course if you're forgotten everything from this class, which is going to happen pretty quickly. So in terms of after this class, what this class qualifies you to take, it qualifies you to take Math 142. We call that college math as opposed to college algebra. It's probably the easiest of the courses that you would be able to take after this course. It's a course where you do like money problems, like calculate car payments, house payments. You do probability problems, like if I roll a pair of dice, what's the probability that my dice sum up to a 7? You do like mean, median, and mode statistics, bar graphs, pie charts. You do unions and intersections with sets, which you may have not seen before. Then it's not terribly hard. So there's a lot of like random topics. You do some area and volume problems in geometry. You do Roman numerals. It's just kind of a smattering of different topics. And very definitely, if you want to teach grade school and you want to major in elementary education, that is definitely the math class for you. And a lot of the BSN nursing majors get to take that as well. For a BSN, that would be your last math class. For an elementary education major, after you take Math 142, you take Math 156, then 157. Each of those are like math for elementary education majors. So this Math 142, because it's a little bit lighter course, it definitely won't count for degrees that have any sort of math in them or science in them. Another course that you could take next is Math 151. At GCC, we also offer Math 150. These are considered the same courses. Math 150 is worth 5 credit hours, and you get more class time, but you cover the same material. Math 151, you just move a little bit faster in class. We call this college algebra. And really, that's what this course was designed to prepare you for the best. College algebra will feel a ton like this course. We solve for x, we factor, we do logarithms, we work with negative exponents. All the things that we did in this course will be taught again in that course, and you go a little bit deeper. Definitely business majors, this is the math for you. Psychology majors usually take this too. Generally, most majors in a 4-year degree will take Math 150 or 151. After Math 150 or 151, a lot of psych majors can take Math 172, which is finite math, which is another course where you do house payments, car payments, but you do and you do the probability stuff. There's some overlap between 172 and 142, but you do some other, I'll call them optimization problems, where you're trying to allocate your resources to make the most profit or minimize the most cost minimize cost. Business majors will take Math 212, and again, Math 212 and 213 are the same course, and this is the first semester of brief calculus. So it's a calculus course that's without trig. And then business majors after Math 212, or if they take 213, they likely take Math 218 if you're going to ASU. And 212 or 213 are brief calculus 1, 218 is brief calculus 2. Not all business majors have to take 2 semesters of calculus. Depends what school you go to. ASU, the WP Carey School, wants you to take 2 semesters of calculus. For a lot of students, college algebra, Math 151 is the last math class they take, and they can get their 4-year degree. Another path from Math 151 is you also could take Math 182, which is trig. And trigonometry is something that a computer science or an engineering major would take. And after trig, you can take regular calculus, calculus with trig in it. I'll just call this Calc 1. So Math 142, that's kind of a terminal class, although elementary education majors, terminal meaning you usually don't take another math class after that, unless it's the math for elementary school teachers. Nursing majors can take that. Math 151, most non-engineering, non-science majors, that's not elementary ed or history or nursing, will take this for their degree. Business majors usually have to take brief calculus after this. Psych majors sometimes can get by taking finite math. And if you're an engineering major, this is a path to get to calculus. You could take Math 151 one semester, the following semester take trig, and then take Calc 1. The third course that you qualify to take immediately after this, we might call this pre-calculus, Math 187. It's a tough course, but it's like taking 151 and 182 combined into one class. If you take 187, then you wouldn't take 151, nor would you take 182. That's like taking one class that counts for both of those. And everybody that takes 187, maybe some pharmacy majors don't take another class, but most everybody that takes Math 187 takes the traditional calculus class. Calculus. So I don't know that that's like the most in-depth review of what you need to be thinking about if you're going to take more math. But this gives you some idea of what you can take and some of the paths that it will lead you to. Again, unless you're 100% certain that you're never, ever going to go for a 4-year college degree, then you don't have to worry about taking more math if your degree only requires intermediate algebra. But if there's even the smallest chance that at some point in the future you're going to do a 4-year degree, taking Math 151, if you know you're not going to go into nursing or elementary education, is a safe thing to do. Math 142 isn't so safe unless you know specifically what you're going to do. Most schools, if you take Math 151, they will count it for Math 142 because it's a harder course. Most schools, if you took Math 142 and you needed Math 151, they'd still make you take Math 151. So Math 151 is a little bit safer. And if you took 187, they would count it for any of those courses because they progressively get harder as I move to the right on this paper. Okay, so that being said, I'm going to jump into the review. This was a longish chapter, so it's real easy to forget some of the stuff from the beginning. And one of the very first things that I wrote was a chart like this. And this is supposed to tell me how to reduce the first 3 problems. So, any operation, adding, subtracting, multiplying, dividing, or composition, is okay for me to put on a test, even though the review might not have all the operations. So in the first three problems, actually the first six problems, we're taking two functions and making a new function by combining them either by adding, subtracting, multiplying, dividing, or composing them. And the times that you need parentheses are composition, subtracting, and multiplying. Adding, you don't need parentheses when you're doing it. Dividing, you don't need, but you need a fraction. So I'm going to pull this back and forth as I do the problems. So the first problem in this grouping is the nice kind one, f plus g of x. My template for f plus g says I just need a plus sign, no parentheses. So the first thing I'm going to put is what f is equal to. F is equal to x squared minus 3x. Then I'm going to put the plus sign. Don't need a parentheses, but after the plus sign I need to write what g is equal to, which is 2x minus 6. So I'm going to reduce this. I'm not going to multiply by x. This x in the parentheses just means don't change the x to another letter. And if this factors, I'll factor it, and it does factor, and that will be my answer. So I'm not multiplying everything by x, I'm just not changing the x to a number or another letter. And I'm not taking my answer and setting it equal to 0. So I'm going to write the original problem, which you really don't have to. You can just write what I'm writing to the right of the equal sign. And this factors, my first are a couple of x's, my last have to multiply to negative 6, add or subtract to negative 1. It's going to be plus 2 and a minus 3. So the bad things you can do is you shouldn't multiply by x, even though that parentheses looks like it. It doesn't mean multiply by x. And you also shouldn't do this. If you went x plus 2 equal to 0 and wrote x equal to negative 2, and you did x minus 3 equal to 0 and wrote x equal to 3, if you did those things, you're going to lose at least 2 points. The adding functions, it doesn't ask you to find a value for x. I'm not solving for x, and it'd be absolutely wrong to either multiply by x or write an answer of x equal to negative 2, x equal to 3. If you multiplied by x, or if you did this stuff, you'd lose at least 2 points. Next one, f divided by g. I'm going to form a fraction with the right side of f in the numerator. I'm going to write the right side of g in the denominator. The only hope at reducing is if I can factor and cancel. If it factors and cancels, I need to factor and cancel. If it factors and cancel and I don't, I'll lose points. So form a fraction, I don't need parentheses. Right side of f in the numerator, x squared minus 3x. Right side of g in the denominator, 2x minus 6. And actually both of these factor, and neither is a 2 parentheses factoring, they're both just a common factor factoring. In the numerator, both x squared and 3x have an x, there's a common factor of an x. When I take an x away from the x squared, I'm left with an x. When I take an x away from the minus 3, I'm left with a minus 3. In the denominator, there's a common factor of 2 that I could factor out. When I factor out the 2, I'm left with another x minus 3. So the x minus 3's can cancel. And now I could write my answer. Again, you don't have to write the problem with the answer, but it's not such a bad idea to do that. I'm going to cancel the x minus 3's. I'll be left with x over 2. That's what my key is going to say if this was a test question. If you wanted to, you could move the x to the right of the fraction and leave a 1 behind in the numerator. X over 2 is equal to 1/2 x. And if you just instinctively wrote that because whatever math teacher you had last had the habit of doing that, that's completely fine. Last one, I need parentheses. I'm going to replace the x in the f function with the g function. F composed with g. That open circle doesn't mean multiply, it means composition. I'm going to take the f function. There are two x's. x squared minus 3x. And what I'm supposed to do is replace any x in the f function with the g function. So it's going to be 2x minus 6 and 2x minus 6. This is, in some sense, mean, and I probably wouldn't put something so hard on a test. But on a review, I don't mind making the problems a little bit harder. And the hard part is not getting started. The hard part is the simplifying. So the 2x minus 6 squared is a foiling problem. So I wrote it so I could see the foiling. The firsts are 2x times 2x, which is a 4x squared. The outers are 2x times minus 6, which is a minus 12x. The inners are minus 6 times 2x, which is another minus 12x. The lasts are minus 6 times minus 6, which is a plus 36. So I've did the square part. Now I need to do the multiplying. I need to multiply negative 3 times 2x, and I'll get a negative 6x, and do negative 3 times negative 6, and I'll get plus 18. So I've cleared the parentheses. I need to combine like terms and attempt to factor. So f composed with g of x. The 4x squared won't have anything to combine with it, but I have a minus 12x, a minus 12x, and a minus 6x. And I need to combine minus 12, and minus 6. So minus 12, minus 6 equals to minus 30. So I'm going to get a minus 30x. And then the two numbers without the letters are the plus 36 and the plus 18, and those come out to be a 54. There's definitely a common factor of a 2 that I should absolutely factor out. So I see a common factor. I should always factor out a common factor if I see one. So I'm going to pull out a 2 and be left with 2x squared minus 15x plus 27. Now this is my side work. I'm going to attempt to factor what's left in that parentheses. And it's bottoms up factoring, and I usually do bottoms up factoring off to the side. So I'm going to try to factor 2x squared minus 15x plus 27. Bottoms up, first I multiply. I'm going to multiply the 2 and the 27 and get x squared minus 15x plus 54. Now I know my signs have to be double minus, and I need to get that 15. So I could be minus 1 and minus 54 for my lasts, minus 2 and minus 27 for my lasts, minus 3 and minus 18. 4 doesn't go into it, 5 doesn't go into it, minus 6 and minus 9. 6 and 9 go into 54, and they give me the 15 that I need. So I'm going to write this as x minus 6 times x minus 9. I need to finish up my bottoms up. I started off multiplying by 2. I'm going to end up dividing by 2. First parentheses, x minus 6 over 2, I'm going to write as x minus 3. Second parentheses doesn't reduce, so I bottom up. I'm going to have to write my answer on the next page here. I'll just make my answer go lower. So the best answer, if you got this far and didn't factor this, I'd take a 1 or 2 off. Because anytime a problem is factorable, you're expected to factor it. So I'm going to write as 2 times x minus 3 times 2x minus 9 for my final answer. I'm not multiplying by x, nor am I setting x minus 3 equal to 0 or 2x minus 9 equal to 0. The first 3 problems were just combining the two functions into a new function, not changing the letter to a number. That's why the x is in the parentheses. That just tells us to leave the x alone. Don't change it to a number. And I'm not setting my answer equal to 0. So that's it for problem 3. So the best answer for 3 is going to be have 3 factors, the 2, the x minus 3, and the 2x minus 9. 4 through 6 are easier for me because they have the number in the parentheses. for each one of these problems, what we did when we did them in the section is we pretended it started with an x, should I say. So if problem 4 had an x, what I would do is I'd write the right side of the h function, which is x squared minus 9. I'd put a plus sign, and then I'd write the right side of the k function, which is 3 minus x squared. I can reduce it now, or I can reduce it by changing the x to 2. Generally, it's easier to reduce with a number, and this problem requires me to change the number to 2. So I'm going to do that. It actually will make it less confusing if I actually do that. So to do problem 4, I need to know which x's to change to a 2. So I figured out what h plus k of x is. I think I could actually do this without my calculator for a change. But if you want to use your calculator, it's fine. So this is going to be 4 minus 9 plus 3 minus 4. And then, let me just do that, 4 minus 9 plus 3 minus 4. And I get negative 6. So my whole answer to this problem, I could either just write the answer negative 6 by itself without writing the problem. I could write the problem and then the answer. But I can't say x equal to negative 6 because x actually equals to 2. If I want to include a letter with my answer, it's actually a y. So just writing the number negative 6 is adequate, but writing one of these two are better. For 5, same deal. The problem doesn't start with an x, but it helps me tremendously if I pretend the problem had an x, so I know which x's to change to the number. H divided by k of x, I would do that by forming a fraction with the right side of h in the numerator and the right side of k in the denominator. So to do what I need to do, h divided by k of negative 1, now I know which x's to change to negative 1. This is going to be negative 1 squared minus 9 over 3 minus negative 1 squared. I could do this on my calculator, so I will, but then I'll do it by hand. So on my calculator, fraction, the negative has to be in a parentheses. And if you don't, you'll get the wrong answer. So negative 1 squared minus 9 over 3 minus negative 1 squared. The answer is supposed to be negative 4. To get there by hand, in the numerator, I get 1 minus 9. And in the denominator, I get 3 minus 1. I do the exponents first. 1 minus 9 is negative 8. 3 minus 1 is 2. And negative 8 over 2 is going to be negative 4. So for my answer, I'm going to write the number negative 4. And for my answer, I could just write the number negative 4. Or I can, better yet, I can write the original problem. Say that equals to negative 4. If I want, I can say y equal to negative 4. It would be wrong to say x equal negative 4 because x is equal to negative 1. Problem 6, just like I did 4 and 5, I'm going to do the problem like it had an x to start. So if it said k composed with h of x, I'd write the k function, 3 minus x squared, without the x, and I'd replace the h function with that x. So composition, I always write what's to the left of the open circle. I replace its x with the function that's to the right of the open circle. So I replace the x in the k function with the h function. Now I'm going to do the substitution of the number and simplify. So k composed with h of 0 is going to be 3 minus, I don't really need a parentheses because the 0 is positive, like I did with the negative 1 above. And then I could do this by hand, or I could use my calculator. So this is going to be 3 minus, the parentheses comes out to be negative 9 squared because I get 0 minus 9. So it's going to be 3 minus 81, which is going to be negative 78. It's going to be my answer. So again, if I did this on my calculator and did 3 minus parentheses 0 squared minus 9, my calculator would tell, really, oh, I forgot the squared. Back up, squared. 3 minus 0 squared minus 9 squared, my calculator tells me it's negative 78, and that's what 3 minus 81 is. So for an answer, I can write k composed with h of 0 equals negative 78. I also can say y equal to negative 78. If you just wrote the number negative 78 without any letter, I could live with that. But if you wrote x, it would be wrong because x is 0, and what I get out when I plug in x in is a y. Those were the kind of problems from section 4.1 that will make their way onto the test. The next two problems are from section 4.2. First, I have to determine if a function's one-to-one. A function's one-to-one if all the y's are different. So if I look at problem 7, the y's are negative 1, negative 4, positive 4, and positive 5. So f is 1-to-1. Whereas g, I have y equal to 2 and y equal to 2 on the first and the last point. Because I have duplicate y's, g is not 1-to-1. So the first sentence applies for both the problems, determine which are 1-to-1. The second sentence only applies to problem 7. It says if a function is 1-to-1, find its inverse. You find an inverse of a function written as a set of points by just switching the x's and y's, and we use the inverse notation. So I'm done with problem 8 because the if part doesn't apply to it. But in problem 7, I need to say the inverse of f is, and I'm using the inverse symbol, this negative 1 exponent in function notation means what I'm going to write now is the inverse of f, and it's going to have the points negative 1, 0, negative 4, positive 1, positive 4, 2, positive 5, 3. And that's all there is to do. There's no algebra for either parts of 7 or 8, which makes them hard to give a lot of partial credit. So the instructions will be the same on the test. You can be guaranteed of that. So if a function is written as a set of points, it's 1-to-1 if all the y's are different. It's not 1-to-1 if there's duplicate y's. If it's not 1-to-1, I don't find its inverse. If it is 1-to-1, I use like a negative 1 exponent to say this, what I'm going to write is the inverse of f, and I switch the x's and the y's. The next two problems give me a 1-to-1 function written as an equation and want me to find the inverse. And the steps to find the inverse, what we did when we did this in section 2, 6.2, change the function symbol to y first. So I'm asked to find the inverse of this, and the function notation makes it hard to tell what I'm doing in terms of finding the inverse. So I change the function symbol to y, and then I actually find the inverse. You find inverses by switching x's and y's. So my second step for problem 9 is to switch the x and y. Third step, functions are usually solved for y, so I'm going to solve for y. It's going to take me 2 steps. I'm going to minus 8 from both sides, which will give me x minus 8 equals 6y, and x minus 8. And then I'm going to divide everything by 6. X over 6 I can leave at x over 6, or I can write as 1/6x. 8 over 6 I'm going to reduce to 4/3, and 6 over 6y I'm going to reduce to y. I'm done now. I just need to show that I found an inverse. So I'm going to write the answer using the inverse symbol. You'd lose a point if you stopped right now. It's the correct inverse, but I can't tell by looking at it how it's related to the original problem. So I'm going to write the function name with the negative 1 exponent, and that clues me into what I'm going to write after the equal sign was obtained by switching the x's and y's. So that would be perfect for number 9. This is the answer, the best answer for number 9. I'm going to do the same steps for 10. So for problem 10, which is h of x equals 2x plus 3 over 4, it asks me to find the inverse. So I'm going to change the function symbol to y, get y equals to 2x plus 3 over 4. Step 2, switch my x and my y. X equals 2y plus 3 over 4. Now solve for y. This is the kind of where I needed to solve by cross multiplying, or that I could solve by cross multiplying. So I'm going to write the x as a fraction to help me do the cross multiplying. I'm going to cross multiply up and down. It doesn't matter which side I write things on. So one side I'm going to need 1 times 2y plus 3. The other side I need x times 4, which I write as 4x. 1 times anything is itself, so I get 2y plus 3 equals to 4x. And I'm going to minus 3 and divide by 2. When I minus 3, I get 2y equals 4x minus 3. And then divide by 2, divide by 2, divide by 2. I get y equals to 2x minus 3 halves. So the monster step here was the solving for y. I have my answer. I'm just going to write my answer using the inverse symbol. The inverse symbol is just the -1 exponent included with the function name. So when somebody looks at this answer, they'll know that this function was created from the x function by switching it, from the h function by switching its x's and y's. So that's the answer to 10. So that's the end of section 6.2. The next problems will move on from 6.3. And the next one wants me to sketch a graph of an exponential function. Doesn't have a logarithm. For functions that have an x and an exponent, I look at the exponent, I change the sign of the exponent, find that number on the x-axis, and then find 5 consecutive numbers. So the table I'm going to use is -7, -6, -5, -4, -3. So I changed the sign of the +5 and did 5 consecutive numbers with -5 in the center. Use my table on my calculator now. So mode 7 f of x equals 3, exponent alpha x plus 5, start at -7, end at -3, step 1. So I get -7 and then 0.11, -6.33. I'm rounding, that's okay for graphing. -5, 1, -4, 3, -3, 9. So I'm ready to plot my 5 points and sketch a graph. Most of these exponential functions, their graphs don't go beneath the x-axis, and that's the case here. So I'll find -7 on the x-axis and go up 0.11. 0.11 is, it's positive, so it's up, but it's less than 1. It's barely above the x-axis. The next one, I find -6 on the x-axis and go up a third of the way between 0 and 1. It's slightly higher than the last point, but barely. And then -5, 1 is easy, -4, 3 is easy, -3, 9 is easy. And so usually when I have you do a graph on the test, I give you a blank graph like this, so you're not going to have to draw your own coordinate system. Seems like a reasonable graph. On the right, it goes up forever, and off to the left, it just flattens out. It never actually touches nor crosses the x-axis. So that would be perfectly fine for number 11. I'll do the same sort of thing. I look at the exponent, I change its sign to +4, and I'm going to use the table that has +4 in the middle of the x column. The table I'm going to use for this one is 2, 3, 4, 5, 6. This one would be a kind of a nuisance to do by hand, so I'm going to do the whole table anyways on my calculator. So mode 7, mode 7, f of x is parentheses, fraction 1/3, parentheses, exponent, x minus 4, start at 2, end at 6, step 1. So it's 2 comma 9, 3 comma 3, 4 comma 1, 5 comma 0.33, 6 comma 0.11. It's actually 1/9. It shows me there that it's equal to 1/9. That's kind of how it's showing this fraction. And that's actually 1/3. It shows me that it's a fraction. So easy enough to plot these. 2 comma 9 is up there. 3 comma 3, 4 comma 1. Then I go to 5 on the x-axis and then up 1/3 of the way between 0 and 1. And then 6 and up 1/10 of the way between 0 and 1. And this is kind of the reverse. When you get a fraction base, the graph kind of does the opposite. It flattens out to the right and goes up on the left. I can't remember ever asking a exponential function with a fraction base on a test, but I mean, if you're using your calculator to find the table, it's just not that hard. Doing the table by hand is a little bit trickier when you have a fraction as a base. Ew, nice. 13, I have the answer staring at me. So I give you the formula, which is nice. It means I need to attach numbers to all the letters but one. The first number I see is the initial deposit. The initial deposit as a letter stands for P. The ending of future amount is the A. The 6% is the interest rate. It's the R. I'm going to put it in as a 0.06. The word after compounded is the N. And there's 12 months in a year. So I'm going to plug in 12 for N. And then the last number I see is 25. It stands for years, so it's the time. I'm going to plug these numbers into the formula. I'm going to go A equals to 10,000 for P times 1 plus 0.06 over 12 to the N times T power. So that should do me. If I could just enter that on my calculator, I should get this answer, hopefully. So let me try that. So I have to hit the mode 1, it'll be fine. And now 10,000 times parentheses 1 plus fraction 0.06 over 12, close my parentheses, exponent. So you can see almost I have the whole thing in except for the exponent, and then 12 times 25. So I've entered it essentially perfectly. Hopefully I get that. And I have to round to 2 decimals because it's money. So I look at the number in the third decimal place. That 8 tells me to round the 9 up. The 9 rounds up to a 10. And that's going to carry over and round the 6 up to a 7. So that's perfect rounding. 69.8 cents rounds to 70 cents essentially. So $44,649.70 is perfect for 13. 14 is a simple problem. There's no algebra. I shouldn't even done this on a whole page. So it says write it as a log. So I'm going to write the word log. The E is going to be the base. And I'm going to switch the 2 and the Y. So for this problem, I write the word log. The E is the base of the exponent. It's the base of the logarithm. I switch the 2 and the Y, and this is considered logarithmic form. This is a correct answer. If you remember, log base E is the same as ln, so it would be okay and probably better to rewrite this as the ln of y equal to 2, but both are correct. Log base E and ln mean the same. Log base E is longhand, ln is shorthand. Shorthand is often preferred when you're writing an answer, but they're both okay. 15 through 17 ask me not to use my calculator. Honestly, I don't care if you use your calculator, but I'll do these by hand and then I'll do them on my calculator. 15 is asking the question, the base 2 to what power is 16? The answer is going to be 4 because 2 to the 4th power is 16. So when I go to do this, I could write the problem next to the answer, or I can just write the answer. It's going to be 4. If I pulled my calculator out and did the log base 2 of 16, it's going to tell me it's 4. The next problem is asking the question 9 to what power is equal to 1? And I know that anything to the 0 power is 1. So the answer for 16 is going to be 1. 0, should I say? And again, my calculator should kick that out to me just fine. When I do the log base 9 of 1, it tells me that's 0 anyways. And then 17 is asking the question, 2 to what power is 2 to the 10th? Because 2 to the 10th is equal to 2 to the 10th, the answer is going to be 10. It's not really x equal to 10 because the original problem doesn't have an x, but my rewrite has an x just because it's how I can think of the problem. So that's entering the problem, and I get the number 10. So for each of those problems, I really don't care if you use your calculator. I prefer you to be able to do it by hand. If you're going on to Math 151, depending on who you take for a teacher, some teachers are more strict than others in terms of what you can and can't do with your calculator. So being able to do these by hand can't hurt. 17 wants me to make a graph. Remember, when I find a graph for a logarithm, the first thing I do is find the domain, because that's going to tell me where the graph exists and doesn't exist. I find the domain by taking the argument, setting it greater than 0. So for this problem, the domain is going to be x is greater than 3. And how that's going to show up is the graph is going to only exist to the right of 3 on the x-axis, and anywhere to the left of 3, I'm not going to get any graph anywhere out there. So first step, I found the domain. Second step, write without the log. And solve for x. So this problem was y equals the log base 2 of x minus 3. To write without the log, I want to scratch out the log. In order to scratch out the log, the base remains low, and I switch the x minus 3 with the y. I don't need the parentheses anymore when I do that switching. Now I'm going to add 3 to both sides and get x equals 3 plus 2 to the y. One nice thing about logarithms is I use the same table for every graph. The bad thing is my calculator doesn't do it so well because I'm putting numbers in the y column as opposed to the x. So the table I use for every logarithm has negative 2 to 2 in the x column. To get each of my x's, for the first x, I have to go 3 plus 2 to the negative 2. The second x, I'm going to do 3 plus 2 to the negative 1. And then 3 plus 2 to the 0. 3 plus 2 to the 1. And 3 plus 2 to the 2. So once I enter 1, I could probably just go backwards on my calculator a bunch. So first one, 3 plus 2, up arrow, negative 2. I can't do 13 over 4 so well. I'm going to make it into a decimal, and I get 3.25. I'm going to backwards, delete the negative 2, make it a negative 1. 7 over 2 is 3.5. I hit the SD button to make that into a number I can plot better. Now I'm going to backwards, delete, change the exponent to a 0. 3 plus 2 to the 0 is 4. Now I'm going to change the 0 to a 1. 3 plus 2 to the 1 is 5. And now I'm going to change the 1 to a 2. 3 plus 2 squared is 7. So I'm just going to plot these points and connect them. They shouldn't point me beyond that dotted line. So first point, 3 1/4. 3 1/4 is, about there on the x-axis, and then down 2. And then 3 1/2 is about there, down 1. 4 0, 5 1, and 7 2. Generally, logarithm graphs, they generally shoot down all the way to negative infinity when they get close to that dotted line. And then off to the right, they generally just kind of slowly work their way up to the right and go up forever. That's the classic logarithm graph. And we can get things that aren't the classic graph. If I made the base a fraction, that would kind of make it not so classic. And I mean, I could do things to the argument too to make it not so classic. But in intermediate algebra, this is the style of logarithmic graph that you should be able to do. So first, determine where there isn't going to be a graph by finding the domain. Take the argument, set it greater than 0. Second, scratch out the log and switch, solve it for x. All logarithm graphs, I use the same negative 2 to 2 table, except it's in the y column, so I can't use the table feature on my calculator. Got all the x's by hand. Well, I used my calculator, but I didn't use the table feature on my calculator. Plot the points and connected them. 19, I need to write one logarithm for each letter. Expanding from one log to multiple logs implies you want one logarithm for each letter. So I need one logarithm for the x cubed, one logarithm base 2 for the y to the 4th, one logarithm base 2 for the z squared. Now I need to get signs. The only logarithms that ever get minus signs are those whose letters came from the denominator. So the y logarithm and the z logarithm deserve minus signs. And this is actually an acceptable answer. The instructions don't technically say to use the exponent to multiply rule. So that would be a completely acceptable answer because it's expanded. But it would be better if I used the rule that allows me to make an exponent into a coefficient. But I would give full credit for either answer. So both would be okay. 20, same style of problem. I need to make one logarithm for each letter. The base of the logarithms are 4, so I'm going to make a base 4 for each. I get lazy and don't put the arguments in parentheses when it's a single letter. My calculator needs these to be in parentheses, so if you threw them in parentheses, that's probably better than what I do, but it's common to be a little bit lazy when your argument's just a single letter. And now I need to get signs, and because there's no fractions, no logarithm deserves a minus sign in front of it, which means these things need plus signs. So this would be okay, and it would be better if I made the exponents and the coefficients, even if I didn't take the time to write the parentheses. So a better answer would be the log base 4 of x plus 3 times the log base 4 of y plus 5 times the log base 4 of z. The next problems are going to go in reverse. They're going to give me multiple logs and want me to write them as a single log. For both 21 and 22, to make one logarithm to make 2 or 3 logarithms into one logarithm, I need to make coefficients into exponents first. I'm not sure why that 2 has a line through it, and I haven't been able to figure out why it has a line through it. I try to delete it and retype it, but they're both 2's, the bases. So I make the coefficients into an exponents, and now I can condense the 2 logarithms into one. If there's a minus, I know I need a fraction. If there wasn't a minus, I wouldn't need a fraction. The letter that belongs in the denominator is the letter whose logarithm has a minus in front of it. This is one logarithm that's equal to the original 2. In problem 22, I'd make the coefficient of the logarithms into exponents, giving me an x to the 5th and z cubed logarithms. Still have 3 logarithms. I'm ready to condense them into one logarithm. Because I see a minus, I know I need a fraction. Any letter whose logarithm has a minus sign in front of it belongs in the denominator of a fraction. If the logarithm doesn't have a minus in front of it, that letter goes in the numerator. So again, this is the best answer for 21. And this is the best answer for 22. I guess you could put up parentheses if you really felt like it, but they're okay not to have them when you have just a fraction as the argument as well. 23, because the x is in an exponent, it can be solved 2 ways. You can solve it with logs, or making the bases the same. And in section 6, 7, I showed you both. These are like the first 12 problems in 6, 7. With logs, you would do this. You'd write the word log. The 2's the base. It stays the base. You switch the 16 in the x minus 5. I need to solve for x by adding 5 to both sides. When I do that, I'd get 5 plus the log base 2 of 16 equals to x. And then using that strategy, I'd use my calculator. 5 plus the log base 2 of 16. I get 9 equal to x. I'd check it. I'd go to the original problem and see if I change the x to 9. If I'm left with a true statement, to see if 2 to the 9 minus 5 power, it does equal 16, so my answer is correct, and I'm done with the log strategy. I like that strategy quite a bit. This problem is set up so it's not so hard to do it the other way. I do a prime factor tree for 16. 16 is 2 to the 4th, so I can rewrite this problem as 2 to the x minus 5 equals 2 to the 4th. Since it was easy to make the bases the same, I can drop the bases, set the exponents equal to each other, and get the answer of 9 quicker. Both methods work. Anytime there's an x and an exponent and this problem has an equal sign, logs will always take you to the answer. Making the bases equal, sometimes it's easy, sometimes it's impossible if you get a decimal answer, and sometimes it's just hard if you get a fraction answer. 24 is the case where it's probably easier doing it the log approach, but it can be done without logs, so I'll show you both ways. So solving with logs first, because that's the easier way. So I'm going to write the word log. The 1/2 starts as the base. It needs to stay the base. I'm going to switch the 16 in the x plus 1. So I get the log base 1/2 of 16 equals x plus 1. I'm going to minus 1 from both sides, and I get negative 1 plus the log base 1/2 of 16 equals to x. Then I use my calculator. Negative 1 plus the log base 1/2 of 16. That equals to negative 5, so I get negative 5 equals to x. I should always check before I commit to an answer. I go to the original problem and see if 1/2 to the negative 5 plus 1 power equals to 16. So parentheses, fraction, 1/2, close my parentheses, close my parentheses, exponent negative 5 plus 1 power, and I get a true statement, so I know my answer is correct. That's probably the easier way to do this problem, but I'll show you the other way because it can be done. So I can make the base the same. First I could do a prime factor tree for 16. 16 is equal to 2 to the 4th. So I can write this as 1/2 to the x plus 1 power equals 2 to the 4th. I need to change both sides to have a base of 2. I'm going to rewrite 1/2 as 2 to the negative 1 power. Because they're equal to each other. And now I'm going to multiply the exponents because the 2 has 2 exponents that apply to it. I'm going to multiply them. So I'm going to go 2 to the negative 1 times x minus 1 equals 2 to the 4th by just multiplying those exponents. Now the bases are the same. I can equate the exponents. Negative 1x minus 1 equals to 4. I'm going to add 1 to both sides and get negative 1x equals to positive 5. And then divide both sides by negative 1. And that would give me x equal to negative 5. This, I kind of really only did it for myself for the most part, and for maybe the 2 or 3 of you that could stomach this. But I would expect most of you to do a problem like this with logarithms, because anytime you have an equal sign and an x and an exponent, you can solve with logs. And the next two problems, 25 and 26, I'm going to solve with logs, and it tells me to use logs. So has an x and an exponent, I can solve it with logs. So I'm going to write this as a log base 3 of 6 equals to negative x. I write the word log, the 3 stays low, I switch the negative x and the 6. I want to solve for x before I use my calculator. So this is really the log base 3 of 6 equals negative 1x. So I'm going to divide both sides by negative 1. It doesn't say round. I'll add this here in a bit. Round to 2 decimals. And I'll add that in to the handout because I forgot to put that in. So now I'm going to do this on my calculator. Fraction, the log base 3 of 6 over negative 1. And I get negative 1.63. 0 after the 3 tells me I don't have to round up. So I'm going to get negative 1.63. A squiggly equals because it's rounding. And then the right side comes out to x. I think this is my answer. I should check. I'll check it right up here. I'll see if I change that x, if I change the x to negative 1.63, I get that. Because there's a negative there already and my x is negative. When I enter it on my calculator, I'm going to make the double negative a positive. So I'm just going to go 3 up arrow 1.63 to make that double negative positive. Makes my calculator work easier. It gives me 5.99 equals to 6, and that's close enough. I didn't expect an exact checking, so that's completely fine. 26 is like the word problem strategy that we need, and maybe I'll do the word problem pretty close to this. So this one I need to isolate the exponential function by dividing by 18. Left side I get e to the x. 12 over 18 reduces by 6 to 2/3. So this gives me e to the x equals 2/3. Now I'm going to write it in its log form. The log base e of 2/3 equals to x. I'm going to round this now. So I could go log alpha e of fraction 2/3, and I get negative 0.405. I'm going to round that to negative 0.41. So I'm going to go negative 0.41 is approximately x. Remember, log base e and ln are the same. So if I would have just typed in ln of 2/3, I'm going to get exactly the same number, negative 0.405, easier on my calculator. Better check this because it's not that easy. So for checking, I need to see if 18 times e to the negative 0.41 power is about 12. I'm going to check it into there. I don't expect it to be exactly 12 because my answer is rounded. So I'm going to go 18 shift ln negative 0.41. And I get 11.94, or 11.95 is about 12. And that's close enough for me. If I wasn't happy that this, if I didn't think this was close enough, I could take more decimals. So the ln of 2 over 3. If I would have checked in, if I would have done like this, if I would have done 18 times e to the negative 0.405465, that'd be closer to 12. So if I wanted to, I could go 18 shift ln negative 0.405465. Oh, really? Can't be. Oh, because I didn't have a decimal. Back up. I forgot the decimal point. And then you get much closer to 12. So if you're not comfortable that your checking is good enough, you can recalibrate and use more decimals in your checking. Let me do the word problem that's left. The only word problem in this review that's left is this one. It tells me to round to 1 decimal, so I shall do that. And it's a money problem, and it has the word compounded continuously in it, which automatically means I need the formula A equals P e to the RT. A is the amount of money in the future. P is the beginning dollars or the starting dollars. R is easy, it's the interest rate. So if I look at the first number, it's $1,000, it's going to be the P. The only other number I see is the 6%. It's the R, and I'm going to write it as 0.06. I need to have, or T is the time, I need to have another number, and the triple is the hinge to give me the other number. It gives me tripling $1,000 in the future, and the future amount is going to be $3,000. So algebraically, I'm solving for how long, which is T, and the equation that I'm solving is this: 3,000, which is A, equals to 1,000, which is P, times e to the 0.06 t. To solve this, I do it just like the last problem. I divide to isolate the exponential function. So in this case, I'm going to divide by 1,000. This is going to give me 3 equals e to the 0.06 t. I'm going to write it with a log. The e is going to be the base, and I'm going to switch the 3 in the 0.06 t. Before I use my calculator, I'm going to solve for the letter, so I'm going to divide both sides by 0.06. The left side's going to give me a t, and the right side I can do like this: fraction log base e of 3 over 0.06, and I get 18.31, which rounds to 18.3. Or I can do ln of 3 over 0.06, because that's also going to give me the same answer. Since I have the answer written here, I'll save the time and not check it. I feel like I sold us a little bit short on the solving with logs, so I'm going to make up 2 more extra problems, because these are definitely... Oh, am I right? No, I take that back. I don't think I... This is not where if I sold you short. I take that back. I think that was okay. That was enough. But that's got to be enough. I was thinking this kind of problem. So I'm just going to keep trudging along. I have a few problems left. 27 and 28 are stylistically the same, and I'm going to solve them the same way. I'm going to scratch out the log. In this case, I'm going to leave the 2 low, and I'm going to switch the x and the -1. So for both 27 and 28, I'll do that. Scratch out the log. The 2 stays low. I switch the -1 and the x. 2 to the -1 power is positive 1/2. So I'm going to write 1/2 equals to x for my answer. I should definitely check. So for my checking, I want to see if the log base 2 of 1/2 equals -1. So log base 2 of fraction 1/2. And when I hit equals on that, it gives me -1 equals to -1. So I feel good about 27. Move down to 28. Stylistically the same problem. I'm going to scratch out the logarithm, switch the x minus 1 and the 5, and I'll get 2 to the 5th. I don't need the parentheses when I free the x minus 1 from the log. The left side, 2 to the 5th power, is 32. So this gives me 32 equals x minus 1. I add 1 and add 1. I have 33 equal to x when I check it. Because anytime I solve a problem with an equal sign, it's just not that hard to check it, so I will. So that's the checking. So let me do log base 2 of 33 minus 1. And I get 5 equal to 5. So I know that 33 is a correct answer. 29's different. 29 has one log equal to another log, and we solve those by just setting the arguments equal to each other. There were only a couple of these in the homework, but but they're easy problems. You set the arguments equal to each other and solve for x. I'm going to minus x and add 5 to both sides. There's no factoring because there's no square. Minus, on the left side, the x's cancel. Minus 1 plus 5 is 4. On the right side, 3x minus x is 2x, and the 5's cancel. I divide both sides by 2, and I get 4 divided by 2 is 2 equal to x. I think this is my answer. I should definitely check. I go to the original problem and see if the log of 2 minus 1 equals the log of 3 times 2 minus 5. I can do that without my calculator because this would reduce to the log of 1. And this is a log of 6 minus 5, which is a log of 1. I know that they're going to check. They're actually both going to come out to be 0. If I wanted to, I could just use my calculator. The left side is a log of 2 minus 1, which is 0. The right side is a log of 3 times 2 minus 5, which is also 0. So I've checked with and without my calculator. Without my calculator, I can tell those are equal even if I didn't know they equal to 0. With my calculator, I got them both equal to 0. Last problem, 2 logarithms separated by a minus. I did a couple of extra problems like this when I did the 6-7 section because there's almost guaranteed to be one on the test. First step, use the minus to divide rule to make the 2 logarithms into 1. So I'm going to make this the log base 3 of x plus 6 over x equal to 1. Now I'm going to scratch out the log and switch. I'll get 3 to the 1 equals x plus 6 over x. All 4 of the problems I did by cross multiplying. 3 to the first power reduces to 3, which isn't a fraction. I'm going to make it a fraction by writing it as 3 over 1. And then I'm going to multiply down and get 3 times x, up and get 1 times x plus 6. That's going to reduce to 3x equals x plus 6. Then I'm going to minus x from both sides and get 2x equal to 6. And then divide both sides by 2 and get x equal to 3. Should absolutely check. It's not that hard to check. So before I commit to writing an answer, I'm going to check. And for my checking, I go to the beginning. I'm going to go, is the log base 3 of 3 plus 3 minus the log base 3 of 3, does that equal to 1? So I'm going to enter this on my calculator. Hopefully it kicks back a 1 to me. So log base 3 of 3 plus 3 minus the log base 3 of 3, and I get, oh no, I think I entered something wrong. Let me clear it out and try it again. Oh, it's going to be 3 plus 6. I did enter something wrong. That should be a 6 right there. So do it again. Log base 3 of 3 plus 6 minus log base 3 of 3, and I get 1 equals to 1. So I've checked my work and I know my answer is correct. So there's a lot of problems that have equal signs, and you should check each and every one and shouldn't miss a point at any of those problems, or at least you know your answer is wrong if you just can't figure out the right answer. So this should be it for a lot of you. I would usually, I get 6 or 7 students every semester that take the final exam, so hopefully you're lucky enough not to have to take the final exam. After I grade your test, if you're confused at all as to what your grade would be if you skip the final and what you'd have to get on the final to change your grade, just come and ask me, send me an email, and I'll tell you specifically. So if you're not sure, just come visit me or contact me somehow, and I'll tell you exactly what your grade's going to be if you skip the final and what you'd have to do on the final to change your grade.